I will write number of atoms unshifted. Number of atoms unshifted by the corresponding symmetry operation. Trace per unshifted atom, and finally I will write chi of d, which is a product of these two numbers. Now I have 4 atoms, okay, 4 atoms, and identity is what? Don't do anything. That means no atom is shifted. So number of unshifted atoms is 4. Now if there is an atom which is not shifted, then the identity is atom has 3 degrees of freedom. So identity is having a trace of 3. So 4 into 3 is 12. Now imagine you have a C3 rotation. What is happening to C3 rotation? C3 rotation is about an axis which is passing through the centroid of the triangle, and nitrogen molecule is along the axis. When I rotate, all 3 hydrogens are shifting, but nitrogen is not shifting. So the number of atoms that do not shift is 1 for C3. If it is C3, C3 all in the same class will have the same number of unshifted atoms. Now what about the trace? Trace per unshifted atom in 3 dimension. In 3 dimension, we have a rotation matrix like this: cos theta minus sin theta 0, sin theta, cos theta 0, 0, 0, 1. This is the rotation about z axis by an angle theta. Okay. Now rotation about any other axis can also have the same trace, because one axis to other axis you can similarity transform, and trace is invariant under similarity transform. So I can say that the trace of rotation matrix is 2 cos theta plus 1. Okay. So in general, for rotations, for proper rotations, the trace is 2 cos theta plus 1. But in this case, what is theta? Theta is 120 degrees. So if I put 120, I will get minus 1. So 1 minus 1 is 0. So I have trace per shifted atom in the rotation C3, C32 is 0. What about reflection? Any reflection is about a plane. So let us say you have an xy plane is the mirror. Z goes to minus z. X and y don't change, right? If I take the trace, what will happen? I will have 2 1s and 1 minus 1. Correct? A general reflection, that is reflection through xy plane, I can write it as 1 0 0 0 1 0 0 0 minus 1. If it is around yz plane, then these two will not change, this will change, and so on. So what will be the trace? Trace of all such matrices of reflection is actually equal to 1. So this is 1. But how many are unshifted here for the sigma? Sigma v is always along a mirror passing through one of the vertices and the nitrogen. So nitrogen and one hydrogen will not change, right? The other 2 hydrogens will change. So this is 2. So this is 0 and this is 2. So the character for this molecule is given by 12, 0 and 2. Now let me write something here which I will explain. Z, RZ, x comma y and Rx comma Ry. X square plus y square, z square, x square minus y square, xy, xz, yz. Okay. I will tell you what these symbols mean. Now, first what we will do is we will try to decompose this. There will be a 12-dimensional reducible representation, and it can be put in a block diagonal form where along the block diagonal you have one-dimensionally reducible representation, two-dimensional, one-dimensionally reducible representation, another two-dimensionally reducible. How many times each one of them will be there? So if you have to ask this question, so you should ask what is nu 1? Nu 1 is equal to, how do I get nu 1? 1 by 6, that is the order of the group, into, I am talking about nu 1, so I must consider this vector. Okay, this vector star this vector. So that is, in the first class I have only one element. Character of the first one is 1, character of this is 12, plus in the second one I have two elements, character is 1 and character below is 0, plus in the third column I have three elements, character is 1 and character is 2. So what do I get? 12 plus 6, 18 by 6 is equal to 3. So the first irreducible representation will occur 3 times along the block diagonal. Will occur 3 times along the block diagonal. Second irreducible representation, nu 2 is equal to 1 by 6, 1, 1, 12, plus 2, 1, 0, plus 3, minus 1, 2. So this will occur only once. Nu 2 is equal to 1. Nu 2 is equal to 1. And the third irreducible representation is equal to 1 by 6, 1, 2, 12, plus 2, minus 1, 0, plus 3, 0 into 2. So I will not get anything from here and here, it is simply 2. 4, right? 4. So nu 3 is equal to 4. Now I can say, what have I done? Now I can write down this D as when I say it is in the block diagonal form, in the vector space language it is like a direct sum of those invariant subspaces, correct? So the representation also can be written in the direct sum language. So this essentially means that I have decomposed this D into D1, direct sum D1, direct sum D1, plus d2 plus d3 plus d3 plus d3 plus d3. So you can see that 3 times this will be there, 3 times this will be there, once this will be there, and 4 times this will be there. What does it mean? What does it mean? It means if you take any, for example, let me write down now I can write down a matrix D for sigma 1, let us say, a 12 by 12 matrix. How do I write? There is 1 here, this is 1 block, and all zeros here. Okay, wherever I am not writing, there are zeros. Then there is 1 here, and again there is 1 here. Okay, and so this 1 occurs 3 times, that is first representation. For second representation, it occurs only once. What is the representation corresponding to this sigma in the second representation? That is minus 1. So I will write minus 1 here once. So 3 times this and minus 1 times this. Then I have to write 4 times minus 1 0 0 1, minus 1 0 0 1, minus 1 0 0 1, minus 1 0 0 1. So this will be the block diagonal form, all are zeros. This 1 will occur 3 times, minus 1 will occur once, this will occur 4 times. This is for sigma. If you have C3, this will be same. This is also 1 because for C3, second is also 1, and this one will be those matrix 2 by 2 matrix corresponding to C3, 4 times it will come. So the 12 dimensional representation has a block diagonal form where first irreducible representation occur 3 times. This is 3 times nu 1 is equal to 3, this occurs only once, nu 2 is equal to 2, and this occurs 4 times, nu 3 is equal to 4. Huh? Nu 2 is equal to 1, that is what we have shown. Oh, nu 2 is equal to 1. Okay. So we can write this in a simple way like this. Just for the clarity, I have expanded this. But in general, what we do is we simply say that D is equal to 3 times D1 plus D2 plus 4 times D3. So this is called decomposition of a reducible representation in terms of the irreducible representations. Decomposition of reducible representation in terms of the irreducible representation. Now, if you look at this, if you look at a 3-dimensional vector x, y, z, suppose you take, because this is the coordinates of any atom that you have in the molecule. If you look at this and if you operate identity, rotations, reflections, all kinds of things, then z actually will not change, z will remain the same, and hence you can say that z actually gets transformed as this, because this is as if it is not done anything to that. Identity means you don't do anything to that. On the other hand, if you take this 2-dimensional representation will mix x and y. So when I write x comma y, that means this will be transformed by these two-dimensional representations. I am assuming that the axis perpendicular to the plane containing the hydrogen atoms are is the z axis. So, x and y. Similarly, rz, how do we understand? If I rotate about z axis, I am rotating, you just put the direction of that rotation. Okay. If you put the direction of rotation, then you will see when you reflect, the rotation sense will differ, correct. So, that means the reflection rz will change sign. So, that will be transformed according to this one. Rotation there is no change, but reflection, the sense of the direction will change. So, I will write it as rz here. Similarly, rx, ry also will get mixed up according to third representation. So, these are actually variables which will transform according to these irreducible representations. Now, why this is important to understand is the following. We have written down this decomposition. We have written down this decomposition for the 12-dimensional representation of all the degrees of freedom of NH3 molecule. Now, we can ask a question. All the degrees of freedom, there will be certain translational degrees of freedom, some rotational degrees of freedom, and some vibrational degrees of freedom. For any molecule, you always have 3 translational degrees of freedom corresponding to the translation of the center of mass of the system, and 3 rotational degrees of freedom about the center of mass, and then rest all are vibrational degrees of freedom. So, you have only 6-dimensional representation as far as vibrational degrees of freedom is concerned. Now, if you want to understand what is the vibrational spectroscopy of this molecule, we will be more interested in looking at vibrational degrees of freedom. Now, that can be easily deduced from here, because if you say what are the translation degrees of freedom, this definitely contributes to translation, because translation is translation along x and y. So, this has a translation, this has a translation, this has a rotation, this has a rotation. So, if I want to if I want to ask the following question, that d corresponding to translation can be written as d2 plus d3, okay, because sorry, d1 plus d3, d1 plus d3, because the translations will go according to this group, and this corresponds to the rotational is d2 plus d3, d2 plus d3. So, the translation per and rotation is actually given by d1 plus d2 plus 2 times d3. So, I can immediately write down the vibrational degrees of freedom. The representation for that can be the total d minus d translation plus d rotation, which is equal to, this is 3d and you have a d. So, it is 2 times d1 plus 2 times d2. So, d vibrational degrees of freedom is a direct sum of 2 times d1 plus 2 times d2. So, I do not have to really take another representation corresponding to a 6 by 6 matrix and deduce these numbers. You can do that also. If you take a 6 by 6 representation and then look at decomposition, you will get these values. But if I do it for the full space, then I look at what are all the ways in which translation gets transformed, rotations get transformed, then I can immediately deduce this result. This actually 2 are 1-dimensional representations, there are 2 2-dimensional representations. Whenever I have 2 2-dimensional representations, they corresponds to 4, because each 2-dimensional representation is like 2 levels, 2 energy levels. Okay. So, totally there are 4 here and 2 there, 6 degrees of freedom corresponds to 6 different modes of vibration. Okay. So, this is how we can get the vibrational modes. So, if you are doing an experiment trying to look at vibrational spectroscopy, you will get, how many peaks will you get? How many absorptions you will get? We will not get all the 6. We will get only 4 modes. 2 corresponding to D1 and 2 corresponding to D2. Now, since there is a degeneracy, the frequency of D2 will be same. Unless you perturb the system and then lift the degeneracy, you will only get 4 peaks. You have to lift the degeneracy in order to get 6 peaks. But 6 are contained in this. In 2-dimensional representations, we have degenerate energy states. So, essentially, other frequencies are forbidden. You can also come from quantum mechanics. You solve Schrodinger equation, you get energy levels, and you will see that some energy levels are degenerate. So, this is coming from a symmetry point of view. So, what is allowed energy values of the Schrodinger equation can be estimated or can be shown that these are